The purpose of this lecture is to learn how to use experimental data to determine empirical and molecular formulas of compounds. Okay, this is not anymore about looking at the common charges and predict what the formula is based on those common charges. Here you have to use mass and the mole concept to determine and to derive what the empirical formula is, and then you will be able to calculate the molecular formula given that you have the appropriate data. So there are a few steps that you have to follow to calculate this, and we have everything here. So the first step is to convert percent data, if that's what you have, into mass data. Sometimes that's actually what you have. So let's start with mass data here. So if you have a compound that is A and B, and just A and B, then you have to start with the mass of each one of those elements. In the case that you don't have the mass but you have the percent data, then you have to use the percent data to determine what the mass of those particular elements are there. So the second step is to convert the mass to moles. So you have to divide by the molar mass of A, so that you know the number of moles of A. You divide by the molar mass of B, so that you know how many moles of B you have. Once you have that, you have to divide by the lowest or the smallest number of moles. If they are the same, well, that's it. If not, then you have to look at which one is smaller and then divide by that one. At that point, you are going to obtain the A to B mole ratio on that formula. You're using mass, but you are, remember, elements react in definite proportions. You will obtain a mole ratio in which they appear in that particular compound. Then you have to convert that to the smallest whole numbers, and when you convert to smallest whole numbers, then that gives you the empirical formula. Sometimes when you are doing this, if at this step you obtain whole numbers, then you're good. You go directly to the empirical formula. You don't have to do anything else. That's only if you obtain whole numbers to begin with when you're determining the mole to ratio, the A to B mole to mole ratio. Okay, so how do we use this in a practical way? Let's take a look at here. We have a manganese oxide, and we don't know which one it is, and you cannot say just that, okay, you take manganese and oxygen and then you combine it and you look at common charges, because manganese have about probably about 7 charges, different charges. So manganese will form several different oxides with oxygen. So about you have 3.6 grams of manganese and you have 1.84 grams of oxygen. The way to determine what the empirical formula for this oxide is, you focus first in manganese. In manganese you have 316 grams, correct? Now manganese is 54.93 grams per mole and oxygen is 15.999 grams per mole. Those are the atomic masses that you can get from the periodic table. So go back to manganese. So you have 3.16 grams, you multiply that, you want to know how many moles you have. 1 mole divided by 54.938 grams, they give you 0.0575 moles of manganese. If you do the same for oxygen, then is 184 times 1 mole divided by 15.999 grams, and that is 0.115 moles of oxygen. And this is manganese, no M4. So here is the smallest one, 0.0575. So we take those two and we divide by 0.0575. And when you do that, this number becomes 1. 0.0575 becomes 1. 0.115 becomes 2. So this is manganese. This is oxygen. So the empirical formula for this oxide is Mn, just 1, O2. So that's how you use mass data to calculate the empirical formula of a compound. In this case, once you divide by the smallest one, you already obtain whole numbers. That's what you are aiming for. You need to obtain whole numbers when determining the empirical formula. So another example. Now we have a phosphorus selenide, so that's phosphorus, which is 30.974, and that's grams per mole. Keep that in mind. And then we have selenium, which is 78.971, and that's also grams per mole. Well, those are the atomic masses. Let's keep that in mind. So this phosphorus selenide, and it's just phosphorus and selenium, contains 34.35% phosphorus. 34.35% P, which means that 100 grams of the compound is 35 grams of phosphorus, and the rest, 100 minus 35, is selenium. Okay, you are just, remember, this is phosphorus plus selenium. If you have 35 grams of phosphorus, then the difference is selenium. And this is 65 grams of selenium. Now we start with phosphorus, and then we take 35 grams, multiply that by 1 mole, divided by 30.974, and that is 1.109. And then for selenium, we have 65.65 grams, 1 mole, divided by 78.971, and that is 0.831. Of course, we divide here by 0.831, and that number becomes, the one for phosphorus becomes 133, and the one number for selenium becomes 1. Now here you are facing the situation in which you don't have whole numbers. Okay, that doesn't mean that you are going to round this number. Please do not round. Instead, find a number that you can multiply this so that you get a whole number. Okay, it's 133. You can recognize that 33 as probably 4/3, okay, or the equivalent to 4/3. So actually we have to take those two numbers and multiply by 3. If you multiply by 3, then this number becomes 4, this number becomes 3. So the actual empirical formula for the phosphorus selenide would be P4Se3. Okay, so once again, do not round any number when doing empirical formulas, and the guideline that you have to follow about regarding what number to multiply by is here. So if your ending, if that number that you get is 0.20, then that represents a fraction that is 1/5, so you have to multiply by 5. In our case, we had a number that was finishing in 0.33. The fraction is equivalent to 1/3. You need to multiply by 3. So these are common numbers that you will see that sometimes they could be a little off, not too much. So for example, if in this case you have 0.19, assume that's 0.20. Okay, if it's 0.21, assume again that's 0.20. So that's the kind of thing here. So in 0.50, 0.49, 0.51, well, assume that's 0.50 and then multiply by 2. Okay, so these are the guidelines when you have those numbers that are not whole numbers in that step. Okay, the idea is to produce an empirical formula that has only whole numbers. So this is how you calculate empirical formulas. How you determine molecular formula is a little bit different. Okay, so first of all, you need the empirical formula. Okay, so this is exactly what we've seen. So you start with the mass, then you go to moles, then you obtain the ratio, convert to small whole numbers, and then you get the empirical formula. The extra steps that you have to take to calculate molecular formulas is, well, first, you have to obtain a formula multiplier. And to do that, you need the empirical formula mass, and you need the molecular formula. Sorry, molecular formula, no, molecular mass. Okay, and you divide the molar mass or the molecular mass by the empirical formula mass. That will give you a multiplier, and you will take that multiplier and you multiply the subscript in the empirical formula. So basically, that multiplier that I will call n would be equal to the molar mass divided by the empirical formula mass. And then that number that you obtain there, which is supposed to be another whole number, then you multiply the subscripts in the empirical formula by that number, and then that will represent the molecular formula. So how do we use this? We have this organic compound, the empirical formula is CH2O, and the molar mass is 60 grams per mole. So first step, we already have the empirical formula, so we don't have to worry about that. So if it is CH2O, yes, that is 12 for one carbon, plus 2 times 1 for 2 hydrogens, plus 16 for 1 oxygen. You add all this together, that's 30, of course, grams per mole. Okay? And now, the multiplier, which is n, you take that molar mass that is here, then it's 60 divided by 30, and that's 2. So you take 2 and you multiply your empirical formula by that number. Remember, you are multiplying the subscripts, okay? And that would be equal to C2H4O2. This is the molecular formula for that compound. Pretty easy, huh? But not always the case. We have another example here. Now in this is a little more complex because now it's just not 2 elements present. Now we have 3 elements. We have carbon, hydrogen, and oxygen. So, and then you have to do exactly the same thing for every single element that you have in that compound. So we start with carbon, and then is 28.8 grams of carbon times 1 mole, 12.1011 grams, and this is 0.398. Those are moles, but let's keep with the units for now. Hydrogen is 2 grams, 1 mole divided by 1008, and this is 1984. Oxygen is 19.2, 1 mole divided by 15999, and this is 120. We take all this and we divide by 120, which is the smallest number there. This number becomes 1998, which there you are kind of allowed to say that that's 2. This number here becomes 165, which you are allowed to say, well, this is pretty close to 166, and 120 becomes 1. Okay, you don't have whole numbers here. This number here tells you multiply by 3. If you do that, then this number becomes 6, this number becomes 5, this number becomes 3. The empirical formula is C6H5O3. But we still need to work our way to the molecular formula. So that's the empirical formula, and the mass of the empirical formula is 6 times 12011 plus 5 times 1008 plus 3 times 15.999. and this is equal to about 125 grams per mole. Now you take a look here. The molar mass is 250 divided by 125. That's 2. So the molecular formula is the empirical formula, the subscript in the empirical formula times 2. So we have C12H10O6. And that is our molecular formula. There is still one more complex way to do this, and that comes with combustion analysis. And combustion analysis is something that is used very frequently with organic compounds, because organic compounds are made out of basically carbon, hydrogen, most of the time also oxygen, and then a few other things. But usually is for the carbon and the hydrogen. And what we do here is that if, let's say that organic compound contains carbon, hydrogen, and oxygen, then that's the complex case, because you start with a mass of sample. You need to know that mass of sample, and basically you burn it. Okay, you obtain a mass of CO2 and a mass of hydrogen, because that's the products that you obtain when you burn this organic compound in oxygen. With the mass of CO2 and the mass of hydrogen, you can obtain the mass of water, sorry. You can obtain the respective masses of carbon and hydrogen. And if you have the mass of carbon and the mass of hydrogen, and you initially had the mass of sample, you can subtract that for the mass of oxygen. Okay, you find oxygen by difference. Okay, from there, this is just how you obtain the mass data, because from there you do exactly the same we've been doing so far. Okay, you have the mass of carbon, you have the mass of oxygen, mass of hydrogen. You divide by the corresponding atomic masses, and then you obtain moles of carbon, moles of oxygen, moles of hydrogen, and then you go by the process of finding the whole number ratio. Okay, and with that, the empirical formula. If you are to calculate the molecular formula, then exactly the same thing that we've done before. So the combustion analysis is just one way in which you can obtain the mass data to calculate these formulas. Now, this is a little more complicated, and I actually don't like very complicated things. So let's say we have a simpler approach. Let's say that our organic compound only has carbon and hydrogen. That simplifies a lot of things, because we can actually forget about the mass of sample. We don't need it. If we have the mass of CO2 and we have the mass of water, that's all we need to perform the analysis. Because from the mass of CO2 and the mass of water, the easiest way to go by is to calculate the number of moles of CO2 and the number of moles of water. And based on that, and based on the molar relationship that carbon and hydrogen have with those corresponding molecules, then the moles of carbon would be equals to the mole of CO2, and the moles of hydrogen are twice the moles of water, because remember here water, right? 1 mole of water contains 2 moles of hydrogen. Okay, so the moles of hydrogen twice the moles of water, and then from there it's exactly the same we've been doing. So how about we solve this problem? We have phenanthrene, which is a hydrocarbon that is found in cigarette smoke, and when you do the combustion analysis, you obtain 3.46 grams of CO2 and 0.51 grams of water. The molar mass of phenanthrene is 178.2. What is the molecular formula of phenanthrene? So remember, we are going from CO2, from grams of CO2, we go to moles of CO2, and then we go to moles of carbon. Okay, at that point we have moles of carbon. We don't have to do anything else. We just do our analysis as we've been doing. So how many grams of CO2 we have? Okay, we start with 346 grams of CO2, and then is 1 mole of CO2 is 44 grams of CO2. That takes care of that. Then in each mole of CO2 we have 1 mole of carbon. and after this we obtain 0.0786 moles of carbon. That's carbon. For hydrogen, we start with water, and in water we have 0.51 grams, and then 1 mole of water has a mass of 18 grams, and there are 2 moles of hydrogen in 1 mole of water. And that gives us as a result 0.05767. Okay, at this point we have to divide by this number 0.0567, and doing that will give you give us as a result that this is 1.39, and we can round this to 140, and this becomes 1. Okay, so to make this a whole number, then we have to multiply by 5. Okay, so carbon is 140 times 5, and that is 7, and hydrogen is 1 times 5, that's 5. The empirical formula is C7H5, and the mass for this empirical formula is 7 times 12 times 5 times 1008. And that would be equal to about 89 grams per mole, and the multiplier is going to be 178.2 divided by 89, and that is equal to 2 again. So the molecular formula, we take the empirical, multiply the subscript by 2, so phenanthren is equal to C14H10. That would be the molecular formula for phenanthren, and that's it for today.